Welcome to The Explainer. Today, we're taking a fascinating journey straight down to the absolute bedrock of modern computing. We spend all day interacting with the familiar macro-level world of software. We're clicking buttons, streaming videos, typing away. But underneath all of that seamless experience lies a micro-level world of processor execution that is completely hidden from view. So let's dive right in and translate exactly what's happening under the hood.
Seriously, think about a high-level command for a second. When your computer encounters a simple algebraic equation, like x equals x plus y, what is it actually doing? How does that abstract human-level logic translate into the physical, hidden language of the computer's processor? Well, it's not magic, that's for sure. It's a highly structured series of microscopic steps, and today we're going to decode that entire translation process.
Here's a quick roadmap of how we'll demystify this hardware-software boundary. We're covering the computer's hidden language, the anatomy of an instruction, the instruction toolkit, how x86 stacks up against ARM architectures, and finally, controlling the flow.
All right, Section 1, the computer's hidden language. When you use a high-level programming language, something like C++ or Python, very little of the actual underlying machine architecture is visible to you. You're basically completely insulated from the raw hardware.
But there is one crucial layer where the computer designer and the computer programmer view the exact same machine. We call this the machine instruction set. The operation of literally any processor is entirely determined by the instructions it executes. This instruction set takes your concise algebraic formulas, like our x plus y example, and translates them into the most basic register movements. From a designer's perspective, implementing a processor is largely just the task of bringing this specific collection of commands to life.
Moving on to Section 2, anatomy of an instruction. Let's put one of these microscopic commands under the microscope. Deep within the computer, every single instruction is represented by a sequence of bits, and these bits are divided up into fields. Now, the absolute most crucial field is the opcode. Think of the opcode as the verb of the machine language. It dictates the specific action taking place, like add or load. And hey, if the opcode is the verb, then the nouns are the operands. Operands are basically your source data, the memory addresses, or the destinations that your verb is acting upon.
To really visualize how these verbs and nouns are packaged, imagine a simple 16-bit instruction format. The 16 bits are strictly partitioned. You might have an initial 4-bit chunk dedicated purely to the opcode, followed by two 6-bit fields for the operand references. During execution, this whole instruction is read into an instruction register. The processor then physically extracts these specific bits so it knows exactly what operation to perform and exactly which memory locations or processor registers actually hold the data. It's like a giant, incredibly fast puzzle. So, the really cool part is how this actually runs in sequence. It follows this relentless, continuous instruction cycle. First up, the instruction fetch pulls the sequence of bits from memory. Second, instruction operation decoding looks at that opcode to figure out what the heck to do. Third, operand address calculation determines exactly where the source data lives. Is it in main memory, virtual memory, a register? Step 4 is the actual data operation, doing the math. And finally, Step 5, the operand store takes that hard-earned result and places it right in its target destination.
Which brings us to Section 3, the instruction toolkit. Because to be fully functional, a processor needs a specific set of tools to accomplish whatever wild data processing task a programmer might throw at it. A practical computer organizes its capabilities into 4 core categories. First, you have data processing, which includes your arithmetic and logic instructions for computing numbers or manipulating bits. Second is data storage, covering instructions for moving data in and out of registers in memory. Third, data movement, which handles your input-output devices, transferring programs in and spitting results back out to the user. And fourth, control. These are the test and branch instructions that actually let a program make decisions and shift gears.
Now, here's where it gets really interesting. How designers handle those nouns, the operands. There's a huge design choice around how many addresses one single instruction should contain. If you use 3 addresses, you can say add B and C and store the result in A. Super efficient for the programmer, right? But 3 address formats require a really long instruction bit length, which isn't great. 2 addresses are much more standard, where 1 address does double duty as both source and destination. Even simpler is 1 address, which relies on a default hidden register. And amazingly, you can even have 0 address instructions. This operates entirely on a stack structure. Basically, fewer addresses means simpler, shorter instructions, but it also means your program is going to need a lot more total instructions to get the job done.
Let's look at Section 4, x86 versus ARM architectures. This is where we see how all this theory builds into the real world, comparing the two dominant architectural dialects interpreting these instructions today.
These two take radically different approaches. Think of the x86 architecture like a heavy-duty multi-tool. It offers a very complex array of operations and supports an impressive variety of specific data types, from basic bytes all the way up to huge 128-bit types for multimedia. It's built for raw power and backwards compatibility. On the flip side, the ARM architecture acts much more like a streamlined scalpel. It heavily limits operations. Arithmetic is only performed on registers, and it relies strictly on separate load and store instructions to even touch memory. But that simplicity makes ARM incredibly power efficient, which is exactly why it absolutely dominates your smartphone right now.
Finally, Section 5, controlling the flow. Because programs almost never run in a straight, boring line. They have to manage complex decisions, loops, and jumps.
Just think about the rigid structural complexity of static data types, the highly specific byte widths a processor fundamentally understands, versus how a program behaves dynamically. When a program jumps to a new procedure, it doesn't just lose its place, it creates what's called a stack frame. It pushes parameters, local variables, and crucially, the return address right onto this stack. This stack grows and shrinks dynamically as procedures call other procedures, allowing the computer to perfectly retrace its steps when the math is all done. It's this beautiful contrast between static data and totally fluid execution.
And this dynamic flow is managed by just a few key instructions. Branch or jump instructions update the program counter to execute loops or make decisions, often conditionally, based on a test. Skip instructions do exactly what they sound like. They hop right over the next command. And procedure calls utilize that stack structure we were just talking about to reuse entire blocks of code and return safely. Together, these tools break impossibly complex tasks into tiny executable pieces.
Which brings us to a really fascinating reality from our source material. Machine language programmers are rare to the point of non-existence. Honestly, while these raw, binary machine instructions are the absolute bedrock of all computing, almost no human actually writes code at this microscopic level anymore. High-level languages compile down into this format for us. We're all just standing on the shoulders of the instruction set.
So as we wrap up this explainer, consider this. Billions of these invisible, microscopic translations, fetching, decoding, calculating, and storing are happening every single second inside your device right now. What hidden 16-bit or 32-bit instructions are frantically fetching the very pixels rendering this information on your screen? It's an immense, silent symphony powering our entire digital world. Thanks for joining me today, and keep questioning the technology hidden right in front of you.